Welcome to this lecture on ordinary differential equations. Today we are going to explore a beautiful and powerful mathematical technique known as the variation of parameters. If you have ever wondered how to solve differential equations when the external forces are too complex for basic guessing methods, you are in the right place. Let us dive in and build your understanding from the ground up. Now that we know our topic, let us understand the core idea behind it. Imagine you have a basic recipe for a plain vanilla cake. This represents the natural, undisturbed state of a system, which we call the homogeneous solution. Now, suppose you want to add complex new flavors like chocolate swirl. Instead of throwing away your plain cake recipe and inventing a new one from scratch, you simply vary the amounts of the ingredients. In differential equations, when an outside force pushes on a system, we do not guess a completely new formula. Instead, we take the constant numbers from the natural bouncing formula and allow them to change or vary over time. Building on that analogy, let us look at how we set up the mathematics. We start with a standard linear, second-order, non-homogeneous differential equation. The right side of this equation has a forcing function, which represents the external push or pull driving the system. To use our method, we first pretend this external force is zero. This gives us the associated homogeneous equation. By solving this unforced equation, we find the complementary solution, which contains two fundamental solutions multiplied by fixed constants. These constants are exactly what we will be transforming into variable functions to account for the external force. This brings us to the mathematical heart of the method. The variation of parameters formula gives us a direct way to find those unknown variable functions. Conceptually, this formula comes from forcing our proposed solution to satisfy the original differential equation while keeping the algebra manageable. Let us look at the symbols. The capital W is the Wronskian, a special determinant that measures whether our two fundamental solutions are truly independent. The functions u1 and u2 are the unknown parameters we need to find. The functions y1 and y2 are our fundamental solutions, and g of x is the external forcing function. If the external force increases, the rate of change of our parameters increases proportionally. Before we move on to a concrete example, let us visualize what these formulas are actually doing. Look at the graph on your screen. The dashed blue line represents the homogeneous solution, which is the natural, unforced bouncing behavior of the system. The solid red line is the non-homogeneous solution, showing the system's actual behavior when the external force is applied. The arrows between them represent the varying parameters. They act as a mathematical bridge, stretching and modifying the natural behavior to perfectly match the forced behavior. It is not an entirely new wave, but a dynamically adjusted version of the original. Now that we have seen the formula and its visual meaning, let us apply it to a real problem. We want to solve a differential equation where the forcing function is the secant of x. Simpler guessing methods completely fail here. We are given the second derivative of y plus y equals secant x. Our first step is to find the homogeneous solution by setting the right side to 0. The characteristic equation gives us imaginary roots, which correspond to the cosine and sine functions. These are our fundamental solutions. Next, we calculate the Wronskian by taking the determinant of these functions and their derivatives. Thanks to a fundamental trigonometric identity, the Wronskian simplifies beautifully to exactly 1. Continuing with our solution, we now use the formulas we learned earlier to find the derivatives of our unknown parameters. For the first parameter, we plug in negative sine x, the second function, and our Wronskian of 1. Since secant is 1 over cosine, this simplifies to negative tangent x. Integrating negative tangent gives us the natural logarithm of the absolute value of cosine x. For the second parameter, we plug in cosine x and secant x. These two functions are reciprocals, so they perfectly cancel each other out, leaving us with just the number 1. Integrating the number 1 with respect to x simply gives us x. We are now ready to assemble our final answer for this problem. We construct the particular solution by multiplying our first parameter by the cosine function and our second parameter by the sine function. Adding these together gives us the specific response to the secant forcing function. Finally, we write down the complete general solution. This is always the sum of the complementary solution, which represents the natural bouncing, and the particular solution, which represents the external pushing. Physically, this final equation describes every possible state of the system under the influence of that specific external force. Let us solidify our understanding with a second, slightly more complex example. Here, the forcing function is Euler's number raised to the power of x, all divided by x. Again, we start by setting the right side to 0 to find the homogeneous solution. The characteristic equation is a perfect square, giving us a repeated root of 1. Because the root is repeated, our first fundamental solution is the exponential function, and the second is x times the exponential function. We then calculate the Dvorskian using the product rule for the derivatives. After expanding and cancelling terms, we are left with a clean exponential function, e to the power of 2x, for our Dvorskian. Moving forward with this rational exponential problem, we apply our formulas to find the parameter derivatives. For the first parameter, we set up the fraction carefully. The x in the numerator cancels with the x in the denominator of the forcing function. Dividing the remaining terms by the Wronskian leaves us with exactly -1. Integrating -1 gives us -x. For the second parameter, we set up the next fraction. Multiplying the exponential terms in the numerator gives us e to the power of 2x, which perfectly cancels with the Wronskian in the denominator. We are left with 1 divided by x. Integrating this gives the natural logarithm of the absolute value of x. Let us wrap up this second example by building the final equation. We assemble the particular solution by multiplying our newly found parameters by their respective fundamental solutions. This gives us -x times e to the power of x plus x times e to the power of x times the natural logarithm of x. We then add this to our complementary solution to form the complete general solution. Notice that the first term of our particular solution actually overlaps with the natural behavior of the system. Physically, this final expression captures exactly how the system behaves under this unique non-standard stress. Now that you have successfully used the formula twice, let us look under the hood and prove exactly where it comes from. We begin our derivation by proposing that the particular solution looks just like the complementary solution, but with variable functions instead of constants. To plug this into our differential equation, we need its derivatives. We take the first derivative using the product rule, which generates 4 separate terms. If we take the second derivative right now, the math will become an absolute nightmare. To prevent this, we make a strategic mathematical choice. We force the terms containing the derivatives of our unknown functions to add up to exactly 0. This brilliant constraint simplifies our first derivative immensely. Continuing with our derivation, we now have a much simpler first derivative. We can safely take the second derivative using the product rule once again without creating a massive algebraic mess. The next step is to substitute our proposed solution, its simplified first derivative, and its second derivative back into the original non-homogeneous differential equation. Once we do this, we group all the terms multiplied by our first parameter together and all the terms multiplied by our second parameter together. Because our fundamental solutions inherently solve the unforced equation, these massive groups of terms perfectly cancel out to 0. This is the magic of the method revealing itself. We have reached the final stage of our derivation. After all that massive cancellation, we are left with a beautifully simple equation relating the derivatives of our unknown functions to the external force. But we have 2 unknowns, so we need 2 equations. We bring back the strategic constraint we chose earlier. Together, these form a system of 2 algebraic equations. By solving this system using Cramer's rule from linear algebra, the Wronskian naturally appears in the denominator. This gives us the exact, explicit formulas for the derivatives of our parameters. And that is how the variation of parameters formula is born. It is a perfect blend of calculus and linear algebra. We have covered a lot of ground today. So let us summarize the key takeaways. First, the variation of parameters is a universal method that guarantees a solution for any continuous forcing function, unlike simpler guessing methods. Second, the core philosophy is to transform the fixed constants of a natural system into variable functions to handle external forces. Third, the Wronskian plays a critical role in ensuring our fundamental solutions are independent and our formulas work. You have now mastered both the application and the derivation of this powerful mathematical tool. Thank you for joining me in this lecture.